The universe whispers its secrets in the language of light, but perhaps no mystery has captivated the human imagination, quite like time itself. That invisible river carrying us from moment to moment, that silent metronome keeping the cosmic beat, that elusive dimension that flows around us, yet remains forever, just beyond our grasp. Welcome to the weary researcher. Tonight, we drift gently into the realm where physics meets philosophy, where Einstein's gentle genius rewrote the very fabric of reality, and where the impossible becomes merely improbable. And if you find this subject fascinating or enjoy these videos, please consider subscribing. It helps others interested in this topic find it as well. Close your eyes if you wish, let your breathing slow, and prepare to journey through the strange science of time. We'll explore how a young patent clerk in Switzerland discovered that time isn't the steady, universal constant we thought it was, but rather a flexible, malleable dimension that bends and stretches like warm honey in the cosmic breeze. We'll uncover why nothing can travel faster than light, how gravity can slow the passage of time, and whether the dream of time travel might one day become reality. This is a story written in mathematics but felt in wonder, proven in laboratories but experienced in starlight. It's the tale of how we learned that time itself is relative, that simultaneity is an illusion, and that the universe operates on principles so beautifully strange they seem like poetry written by the cosmos itself. From the ticking of atomic clocks to the dance of distant galaxies, from the paradox of twins aging at different rates to the possibility of closed time-like curves, we'll explore how Einstein's theories continue to shape our understanding of existence itself. So settle in, dear traveller, as we embark on this gentle voyage through space-time. We'll move at the speed of understanding rather than light, pausing to appreciate each elegant insight, each mind-bending consequence of living in a universe where time is not what it seems. Whether you're seeking rest or revelation, comfort or curiosity, you'll find that the strange science of time offers both wonder and peace in equal measure. The clock may tick steadily beside you, but tonight we'll discover that time itself dances to a far more mysterious rhythm. Looking at Einstein's revolutionary understanding of time as our foundation, let's explore how his insights into the nature of time and space continue to reshape our understanding of reality itself. We've seen how Einstein showed us that time isn't the steady, universal river that Newton imagined, but rather a flexible dimension woven together with space into what we call space-time. Now we'll delve deeper into the profound implications of this discovery and how it transforms everything from our daily lives to our cosmic perspective. Einstein's special theory of relativity, published in 1905, fundamentally changed how we think about simultaneity, the very concept of now. In Newton's world, if two events happened at the same time, they happened at the same time for everyone, everywhere. But Einstein showed us something far more subtle and strange. Simultaneity is relative. Events that appear to happen simultaneously to one observer may occur at different times for another observer moving at a different speed. This isn't just a measurement problem or an illusion, it's a fundamental feature of how time actually works in our universe. Consider this thought experiment. Imagine you're standing on a train platform, watching a train speed by. In the exact middle of that train, a light bulb flashes. From your perspective on the platform, you see the light reach the front and back of the train at the same time. But from the perspective of someone sitting on the train, the light reaches the back of the train first, then the front. Both observations are equally valid, equally real. There's no universal, correct answer about which event happened first. This is the relativity of simultaneity, and it means there's no cosmic clock ticking away the same universal now for everyone in the universe. This revelation has profound implications for how we understand causality and the flow of time. If simultaneity is relative, then the very notion of a universal present moment begins to crumble. Different observers, moving at different speeds, will have different definitions of what constitutes now. This leads us to what physicists call the block universe, or eternalist view of time, where all moments in time, past, present, and future, exist equally. In this view, time doesn't flow like a river carrying us from past to future. Instead, we exist as four-dimensional objects stretched through space-time, with our consciousness somehow creating the illusion of temporal flow. The mathematics behind these concepts, while elegant, reveal the deep strangeness of our universe. The Lorentz transformation equations show us exactly how time dilates and space contracts as objects approach the speed of light. These aren't just abstract mathematical constructs. They're descriptions of physical reality that have been confirmed countless times through experiment. When particles in accelerators reach 99% of light speed, their internal clocks slow dramatically compared to laboratory clocks. When atomic clocks are flown around the world on airplanes, they return having ticked at slightly different rates than identical clocks left on the ground. But Einstein didn't stop with special relativity. His general theory of relativity, completed in 1915, went even further, showing that gravity itself is a manifestation of curved space-time. In this framework, massive objects don't pull on other objects through some mysterious force. They bend the very fabric of space and time around them. What we experience as gravitational attraction is actually objects following the straightest possible paths through curved space-time. Much like how a marble rolls along a curved surface, this geometric view of gravity has equally profound implications for time. Just as motion affects the passage of time, so does gravity. Time runs more slowly in stronger gravitational fields, a phenomenon called gravitational time dilation. This means that time passes slightly more slowly for someone standing at sea level compared to someone on a mountaintop. The effect is tiny, but it's real and measurable. GPS satellites orbiting high above Earth where gravity is weaker experience time running slightly faster than clocks on the surface. Without corrections for both special and general relativistic effects, GPS navigation would accumulate errors of several kilometers per day. These discoveries about the nature of time have revolutionary implications for our understanding of the universe's structure and evolution. If time is intimately connected to space and gravity, then the expansion of the universe isn't just about galaxies moving apart through space, it's about space itself expanding, carrying galaxies along with it. The Big Bang wasn't an explosion in space, it was an expansion of space itself, and by extension, of time itself. Before the Big Bang, there was no before in any meaningful sense, because time itself began with the universe. Einstein's insights also opened the door to some of the most exotic predictions in physics. Black holes, regions where gravity becomes so strong that space-time curves back on itself, create such extreme time dilation that time appears to stop at the event horizon from the perspective of outside observers. Near a black hole, the difference in gravitational pull between your head and feet, called tidal forces, would stretch you into a long, thin shape, a process physicists somewhat morbidly call spaghettification. Even more remarkably, Einstein's equations allow for the possibility of closed time-like curves, paths through space-time that loop back to their own past. While such structures would create paradoxes that violate our understanding of causality, they're mathematically consistent with general relativity. Theoretical constructs, like wormholes, bridges connecting distant regions of space-time, might in principle allow for faster-than-light travel, not by exceeding the speed limit, but by taking a shortcut through the geometry of space-time itself. The experimental confirmation of Einstein's theories continues to this day, with increasingly sophisticated tests revealing the subtle effects of relativity in everyday phenomena. The global positioning system wouldn't work without accounting for relativistic effects. Particle accelerators rely on relativistic mechanics to predict how particles behave at high energies. Even the internet depends on precise timing that requires relativistic corrections. Recent developments in physics have pushed Einstein's insights even further. The detection of gravitational waves, ripples in spacetime itself, caused by accelerating masses, has opened an entirely new window onto the universe. These waves, predicted by Einstein over a century ago, were first directly detected in 2015 by the LIGO observatories. When two black holes spiral into each other and merge, they create distortions in spacetime that propagate outward at the speed of light, stretching and compressing space by incredibly tiny amounts as they pass by Earth. The study of time in quantum mechanics adds another layer of complexity to our understanding. While general relativity treats time as a smooth, continuous dimension, quantum mechanics suggests that, at the smallest scales, space and time might be quantized, made up of discrete units. The search for a theory of quantum gravity, which would unify Einstein's geometric view of spacetime with the probabilistic nature of quantum mechanics, remains one of the greatest challenges in modern physics. As we continue to probe the deepest mysteries of time and space, we find that Einstein's revolutionary insights continue to guide us toward ever more profound questions. Is time fundamental to the universe, or does it emerge from something more basic? Are there multiple dimensions of time, just as there are multiple dimensions of space? Could the universe exist in a state where cause and effect operate differently than we experience them? These questions remind us that our journey into understanding time is far from over. Einstein's theories gave us a new framework for thinking about reality, but they also revealed how much we still don't know. Every answer leads to new questions. Every solution opens new mysteries. And perhaps that's the most beautiful aspect of Einstein's legacy. Not just the answers he provided, but the deeper questions he taught us to ask about the nature of time, space, and existence itself. The profound implications of Einstein's work extend beyond physics into philosophy, challenging our most basic assumptions about the nature of reality and our place within it. If time is not the universal constant we once thought, if simultaneity is relative, if the past and future exist as concretely as the present, then what does this mean for free will, for consciousness, for the very meaning of existence? These are questions that continue to inspire scientists, philosophers, and dreamers as we push ever deeper into the strange and wonderful universe that Einstein helped reveal to us. When scientists first began measuring the speed of light with unprecedented precision in the late 1800s, they stumbled upon something that would shake the very foundations of physics. You see, they expected to find that light behaved like everything else in the universe, obeying the simple rules of motion that Newton had laid down centuries before. But what they discovered instead was so strange, so counterintuitive, that it would force humanity to completely reimagine the nature of time itself. Let me tell you about two men who accidentally stumbled into one of the greatest mysteries in physics. Albert Michelson and Edward Morley weren't trying to revolutionize our understanding of time when they set up their elaborate experiment in 1887. They were simply trying to measure something that everyone believed existed: the luminiferous ether, a mysterious substance that scientists thought filled all of space and carried light waves the way water carries ripples. Picture this for a moment. You're standing on the deck of a moving ship, throwing a ball in the direction the ship is travelling. To someone watching from the shore, that ball appears to move faster because its speed combines with the ship's speed. Now throw the ball in the opposite direction, and it appears slower to that same shore observer. This is basic physics, the kind we experience every day, and it made perfect sense to apply this logic to light. Scientists reasoned that if Earth was moving through this cosmic ether, then light travelling in the direction of Earth's motion should appear faster, while light travelling against it should appear slower. It was an elegant theory, beautifully logical, and completely wrong. Michelson and Morley built an ingenious device called an interferometer, essentially a sophisticated way of racing light beams against each other. They sent light in perpendicular directions, expecting to detect tiny differences in speed as Earth moved through the supposed ether. They measured and remeasured, adjusted their equipment, and tried again. The result was always the same. No matter which direction light travelled, no matter how Earth was moving through space, the speed of light remained stubbornly, impossibly constant. This wasn't just puzzling, it was deeply disturbing to the scientific community. It was like discovering that no matter how fast you drive your car, a bicycle next to you always keeps pace perfectly. The laws of physics, it seemed, had a very strange exception, and that exception was light itself. For nearly 2 decades, this result haunted physicists. Some proposed elaborate explanations involving ether being dragged along by Earth. Others suggested that perhaps the measuring instruments themselves were somehow contracting in the direction of motion. These ideas grew increasingly complex and unsatisfying, like trying to explain why your shadow always stays the same size by inventing invisible forces that stretch and shrink measuring sticks. Then in 1905, a young patent clerk in Switzerland named Albert Einstein published a paper that would change everything. Einstein had a remarkable gift for cutting through complexity to find elegant simplicity, and he approached this problem with characteristic boldness. Instead of trying to explain away the strange behaviour of light, he embraced it. What if, Einstein asked, the speed of light isn't an exception to the rules? What if it's the most fundamental rule of all? Einstein's insight was breathtaking in its audacity. He proposed that the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. This wasn't just a curious property of light, it was a fundamental constant of nature, as unchanging and universal as the concept of infinity. But accepting this simple statement led to consequences that seemed to defy common sense. If light always travels at the same speed for everyone, then something else had to give, and that something, Einstein realized, was time itself. Consider this thought experiment, one that Einstein himself might have pondered during his daily walks through the streets of Bern. Imagine you're standing on a train platform, watching a train speed past. On that train, someone turns on a flashlight, sending a beam of light toward the front of the train. According to Newton's physics, you should see that light travelling at the speed of light, plus the speed of the train. But Einstein's new theory said something extraordinary. Both you and the person on the train would measure that light beam travelling at exactly the same speed. How is this possible? The answer is that time itself must be flexible. For the person on the fast-moving train, time literally runs slower compared to your time on the platform. Not metaphorically, not approximately, but actually and measurably slower. Their clocks tick more slowly, their biological processes unfold more gradually, their very thoughts occur at a different rate. To them, everything feels perfectly normal, but from your perspective, they've entered a slow-motion world. This isn't science fiction, it's science fact. We've measured this effect with atomic clocks so precise they can detect time differences of billionths of a second. When identical atomic clocks are placed on fast-moving airplanes and compared to clocks that remain on the ground, the flying clocks consistently run slower, just as Einstein predicted. The mathematics behind this phenomenon is elegantly simple, yet its implications are staggering. The faster you move through space, the slower you move through time. At everyday speeds, this effect is negligible. A car travelling at highway speeds experiences time dilation of only a few nanoseconds over the course of a year. But as velocities approach the speed of light, the effect becomes dramatic. Imagine accelerating to 90% the speed of light. Time would slow down so much that what feels like 1 year to you would correspond to more than 2 years for someone at rest. Travel at 99% the speed of light, and 1 year for you becomes 7 years for the rest of the universe. At 99.9% the speed of light, your single year stretches to 22 years in the outside world. This leads us to one of the most famous puzzles in physics, the twin paradox. Picture identical twins, Anna and Maria. Anna boards a spacecraft and travels to a distant star at nearly the speed of light, while Maria remains on Earth. When Anna returns after what feels like a 5-year journey to her, she discovers that Maria has aged 20 years. Anna is now 15 years younger than her identical twin sister. This isn't just theoretical speculation. Every day, particles called muons provide us with natural examples of time dilation. These particles are created when cosmic rays strike Earth's atmosphere, high above our heads. Muons are unstable and typically decay in just 2 microseconds. At that rate, they should never survive the journey from the upper atmosphere to Earth's surface. But they do survive, in large numbers, because they're travelling so fast that time dilation extends their lifetimes dramatically. From our perspective, they live longer. From their perspective, the distance to Earth's surface has contracted, making the journey shorter. Einstein's special theory of relativity revealed that space and time aren't separate entities, but are woven together into a single fabric called space-time. When you move through space, you're also moving through time, and the faster your motion through space, the slower your motion through time. The universe, it turns out, has a cosmic speed limit, and that limit isn't just about motion through space, it's about the very structure of reality itself. But Einstein wasn't finished revolutionizing our understanding of time. Special relativity dealt with objects moving at constant speeds. But what about acceleration? What about gravity? These questions led Einstein to an even more profound insight, one that would take him another 10 years to fully develop, and would reveal that gravity itself is intimately connected to the flow of time. The story of how Einstein discovered that massive objects can warp time itself is a tale of pure thought, mathematical elegance, and experimental confirmation that reads like the finest detective novel. And it all began with Einstein wondering what it would feel like to fall freely through space, a question that would unlock secrets about the universe that we're still exploring today. We've journeyed through the strange landscape of time's speed limit, watched simultaneity crumble, and felt the universe bend around Einstein's elegant equations. But now we arrive at perhaps the most profound revelation of all. Time doesn't just flow differently for moving observers, it flows differently in the presence of gravity itself. Welcome to Einstein's masterpiece, General Relativity, where massive objects don't just bend space, they bend time. Picture this. You're standing at the bottom of a tall building, holding a clock. Your friend stands on the roof with an identical clock. You might assume both clocks tick at the same rate, marking time in perfect synchronization. You would be wrong. The clock on the roof, farther from Earth's gravitational pull, runs slightly faster than yours. The difference is minuscule. We're talking billionths of a second, but it's real, measurable, and utterly fascinating. This isn't science fiction, it's gravitational time dilation, one of the most beautiful predictions of Einstein's general theory of relativity. Time doesn't just slow down when you approach the speed of light, it slows down when you approach massive objects. The stronger the gravitational field, the slower time flows. It's as if massive objects create little valleys in the fabric of time itself, and clocks sitting deeper in those valleys tick more slowly than clocks perched on the surrounding hills. Einstein arrived at this startling conclusion through what he called his happiest thought, the equivalence principle. Imagine you're in a windowless elevator. If the elevator accelerates upward, you'd feel pressed against the floor, just as if gravity were pulling you down. Einstein realized this wasn't just a curious coincidence. Acceleration and gravity are, in a very real sense, the same thing. If you can't tell the difference between being accelerated upward or being pulled downward by gravity, then the laws of physics shouldn't be able to tell the difference either. This insight led Einstein to a revolutionary idea. What we call gravity isn't really a force at all, it's the curvature of space-time itself. Massive objects like stars and planets warp the fabric of space and time around them, creating what we experience as gravitational attraction. Imagine placing a bowling ball on a stretched rubber sheet. The ball creates a depression, and if you roll marbles nearby, they'll curve toward the bowling ball, following the warped surface. This is roughly how massive objects curve space-time, guiding the motion of everything around them. But here's where it gets truly mind-bending. This curvature affects time as much as it affects space. The closer you get to a massive object, the deeper you sink into its gravitational well, and the slower your clocks tick relative to observers farther away. This isn't just a quirk of timekeeping devices, it's a fundamental property of time itself. Your biological processes, radioactive decay, even the vibration of atoms, all slow down in stronger gravitational fields. The effect becomes more dramatic as gravity grows stronger. Near a black hole, where gravity is so intense that not even light can escape, time dilation becomes extreme. If you could somehow hover just outside a black hole's event horizon and watch someone fall in, you'd see their clock slow to a crawl. From your perspective, they'd appear to freeze at the edge of the black hole, their final moments stretched into eternity. From their perspective, however, they'd fall through normally, but they'd never be able to send a signal back to tell you about it. This warping of time has practical consequences here on Earth. The Global Positioning System, or GPS, relies on satellites orbiting about 12,000 miles above the surface. These satellites carry atomic clocks that must be incredibly precise to triangulate your position accurately. But because they're farther from Earth's centre, they experience slightly weaker gravity, and their clocks run about 45 microseconds per day, faster than identical clocks on the ground. If engineers didn't account for this relativistic effect, GPS would accumulate errors of several miles per day, making the system useless for navigation. The mathematics behind gravitational time dilation are elegant in their simplicity. The time dilation factor depends on what physicists call the gravitational potential, essentially how deep you are in a gravitational well. The formula shows that time runs slower by a factor proportional to the difference in gravitational potential, divided by the speed of light squared. Because the speed of light is such an enormous number, and because gravitational potentials in everyday life are relatively small, the effects are tiny, but they're real, and they're measurable. Scientists have confirmed gravitational time dilation with extraordinary precision. In one famous experiment, physicists Pound and Rebka used the radioactive decay of iron atoms to measure time dilation over a height difference of just 22.5 meters. Even across this tiny distance, they detected the predicted slowing of time in the stronger gravitational field at the bottom of their Harvard University tower. More recently, optical atomic clocks have become so precise that they can detect gravitational time dilation across height differences of just a few centimeters. But gravitational time dilation isn't just about clocks running at different rates. It fundamentally alters our understanding of simultaneity and causality. Events that appear simultaneous to an observer in weak gravity might not appear simultaneous to an observer in strong gravity. This creates what physicists call gravitational redshift. Light climbing out of a gravitational well loses energy and shifts toward longer, redder wavelengths, while light falling into a gravitational well gains energy and shifts toward shorter, bluer wavelengths. The implications extend far beyond Earth in the extreme environments around neutron stars, where gravity is billions of times stronger than on Earth. Time dilation becomes dramatic. A clock on the surface of a neutron star would run noticeably slower than one in empty space. Near the event horizon of a black hole, time dilation approaches infinity. Time essentially stops from the perspective of a distant observer. This interplay between gravity and time helps explain some of the most exotic phenomena in the universe. When massive stars collapse into black holes, they create regions where space-time curvature becomes so extreme that the normal flow of time breaks down. Inside a black hole, the roles of space and time actually exchange. The radial direction toward the center becomes time-like, meaning that falling toward the center becomes as inevitable as moving forward in time. Gravitational time dilation also plays a crucial role in cosmology. The expansion of the universe itself creates gravitational effects that influence how we observe distant galaxies. Light from ancient stars has climbed out of the gravitational wells of the early universe, carrying information about cosmic history encoded in its frequency shifts. Perhaps most remarkably, recent advances in atomic clock technology have opened new frontiers in testing Einstein's theory. Physicists can now measure gravitational time dilation effects, so small that they occur across distances comparable to the height of a person. These experiments aren't just confirming Einstein's century-old predictions, they're pushing the boundaries of precision measurement and opening new possibilities for detecting gravitational waves, dark matter, and other subtle effects that influence the flow of time. The dance between gravity and time reveals something profound about the nature of reality. Time isn't a universal backdrop against which events unfold. It's a dynamic, malleable dimension that responds to the presence of matter and energy. Every massive object, from atoms to galaxies, participates in this cosmic choreography, warping space-time and influencing the passage of time around it. As we continue to probe the mysteries of gravity and time, we're discovering that Einstein's vision was even more prescient than he might have imagined. The universe isn't just stranger than we think, it's stranger than we can think, a place where time flows like honey near massive objects and races like quicksilver in the void between stars. And in this strange, beautiful cosmos, every tick of every clock tells the story of space-time itself, curved and twisted by the matter it contains, dancing eternally to the rhythm of relativity. This gravitational dance of time connects us to the cosmos in ways both subtle and profound. The very atoms in our bodies, forged in the hearts of dying stars, carry with them the memory of extreme gravitational fields where time flowed differently than it does here on Earth. We are, quite literally, made of space-time that has experienced the full range of the universe's temporal symphony, from the frantic tick of clocks near black holes to the leisurely pace of time in the cosmic void. Now we arrive at something truly extraordinary, a place where the fabric of space-time itself becomes a playground for possibility. We've journeyed through the elegant mathematics of relativity, witnessed time dilation in action, and seen how gravity shapes the flow of moments. But what happens when we push these concepts to their absolute limits? What occurs when space-time becomes so warped, so twisted, that it opens doorways to the impossible? Welcome to the realm of wormholes and closed time-like curves, where the universe's most exotic predictions dance on the edge between science and science fiction. These aren't merely theoretical curiosities gathering dust in academic journals. They represent some of the most profound implications of Einstein's work, suggesting that space-time might be far stranger and more malleable than we ever dared imagine. Let's begin with wormholes, those hypothetical tunnels through the very essence of reality itself. Picture space-time not as a flat sheet, but as a complex, multi-dimensional fabric that can be folded, twisted, and perhaps even punctured. A wormhole represents a shortcut through this fabric, a bridge connecting distant regions of space and time that would otherwise be separated by vast cosmic distances. The mathematics behind wormholes emerges naturally from Einstein's field equations, those elegant formulas that describe how mass and energy curve spacetime. When physicists solve these equations under certain extreme conditions, they discover solutions that describe traversable passages through the fabric of reality. These solutions suggest that if you could somehow construct or find a wormhole, you might step into one end and emerge from the other, having travelled across the galaxy in mere moments, bypassing the usual constraints of light-speed travel. But here's where things become truly mind-bending. Some wormhole solutions don't just connect different places, they connect different times. Imagine a wormhole where one mouth exists in your present moment, while the other mouth opens onto next Tuesday or last week, or the distant future. Such a structure would create what physicists call a closed time-like curve, a pathway through space-time that loops back on itself, potentially allowing travel into the past. The mere possibility of closed time-like curves sends ripples of excitement and concern through the physics community. If such structures could exist and be traversed, they would fundamentally challenge our understanding of causality, the principle that effects follow causes in a logical sequence. With closed time-like curves, you could theoretically influence events that happened before your journey began, creating the kinds of paradoxes that have delighted science fiction writers for decades. Consider the implications. You could potentially deliver information to your past self, warning of disasters that haven't yet occurred from your perspective, but have already happened from the timeline's perspective. You could meet yourself at different ages, observe historical events firsthand, or even attempt to alter the course of history. The very concept stretches our intuition about the nature of time and free will to its breaking point. Yet Einstein's equations seem to permit such possibilities under certain conditions. The Alcubierre drive, proposed by physicist Miguel Alcubierre in the 1990s, represents one attempt to harness these exotic properties of spacetime. Rather than moving through space at faster than light speeds, which relativity forbids, the Alcubierre drive would contract space in front of a spacecraft and expand space behind it, creating a warp bubble that could theoretically travel faster than light, while never actually exceeding the speed of light locally. The mathematics of the Alcubierre drive are elegant and appear consistent with general relativity. A spacecraft riding within such a warp bubble would experience normal physics, with clocks ticking at their usual rate and no sensation of acceleration. Yet from an outside perspective, the bubble itself could traverse vast distances in remarkably short times, potentially making interstellar travel feasible within human lifetimes. However, the practical requirements for creating an Alcubierre drive reveal the enormous challenges involved in manipulating spacetime so dramatically. The energy requirements are staggering, potentially requiring more energy than is contained in entire stars. Moreover, the drive would require exotic matter with negative energy density, a substance that may not exist in nature and certainly hasn't been created in any laboratory. These exotic matter requirements appear throughout many proposed mechanisms for creating traversable wormholes and time machines. To keep a wormhole stable and traversable, you would need to thread it with matter that has negative energy density, creating a kind of cosmic scaffolding that prevents the wormhole from collapsing. This exotic matter would need to violate what physicists call energy conditions, fundamental assumptions about how matter and energy behave in our universe. The search for exotic matter has led physicists to explore some of the strangest corners of quantum mechanics. In the quantum realm, particles and antiparticles constantly pop into existence and annihilate each other, creating what's known as quantum foam. Under certain conditions, this quantum activity can produce regions of negative energy density, at least temporarily and on extremely small scales. Some theoretical proposals suggest that advanced civilizations might find ways to harvest and manipulate this quantum vacuum energy to construct the exotic matter needed for wormholes and warp drives. Yet even if we could somehow obtain the necessary exotic matter, fundamental questions remain about whether the universe would permit paradox-inducing closed time-like curves to exist. Physicist Stephen Hawking proposed what he called the chronology protection conjecture, suggesting that the laws of physics conspire to prevent time travel paradoxes from occurring. Perhaps quantum effects would always intervene to destroy any closed time-like curve before it could be traversed. Or perhaps the universe has built-in mechanisms that ensure consistency even in the presence of time travel. Some proposed resolutions to time travel paradoxes avoid contradictions entirely through the concept of parallel timelines or alternate histories. In this view, travelling to the past would not change your original timeline, but would instead create a new branch of reality. You could interact with past events and alter their outcomes, but these changes would occur in a separate timeline, leaving your original history intact. This many-worlds approach to time travel eliminates paradoxes while preserving the possibility of temporal journeys. The exploration of closed time-like curves has also led to fascinating insights about the relationship between information and space-time. If information could be sent backward in time, it might be possible to solve computational problems by sending the solutions back to yourself before you've finished calculating them. Such scenarios push the boundaries of logic and computation theory, suggesting that access to closed time-like curves might grant almost unlimited computational power. These exotic space-time geometries also appear in the study of black holes, those gravitational monsters where space-time curvature becomes extreme. Inside a rotating black hole, the Kerr solution to Einstein's equations predicts regions where the usual relationship between space and time becomes inverted. In these regions, called ergospheres, the geometry of spacetime is so twisted that remaining stationary becomes impossible, and all paths lead inexorably forward in what was once the spatial direction. Even more remarkably, the complete Kerr solution suggests that the interior of a rotating black hole might contain a ring singularity rather than a point singularity, potentially creating a passage to other regions of spacetime, or even other universes entirely. While crossing the event horizon of a black hole is generally considered a one-way journey, these mathematical solutions hint at possibilities for escape through inner horizons and exotic spacetime tunnels. Of course, the vast majority of these scenarios remain purely theoretical. We have no evidence that traversable wormholes exist naturally in our universe. No confirmed sightings of exotic matter with negative energy density, and no demonstrated methods for creating closed, time-like curves. The energy scales and technological requirements involve dwarf anything within our current capabilities by many orders of magnitude. Yet the mathematical consistency of these solutions within Einstein's framework suggests that our universe's fundamental laws don't absolutely forbid such phenomena. They represent extreme but logically possible extensions of the principles we've already confirmed through countless experiments and observations. In a universe where time can slow down near massive objects, where simultaneity is relative, and where space and time are woven together into a single dynamic fabric, perhaps even stranger possibilities await discovery. The study of these exotic space-time geometries has also provided unexpected insights into the nature of reality itself. By exploring the mathematical limits of general relativity, physicists have gained deeper appreciation for the subtle ways that space, time, matter, and energy interweave to create the cosmos we inhabit. Even if wormholes and time machines remain forever beyond our technological reach, they serve as powerful tools for understanding the fundamental principles that govern our universe. These investigations have also highlighted the deep connections between gravity, quantum mechanics, and information theory, as physicists probe the behavior of matter and energy in extremely curved space-time. They encounter phenomena that blur the traditional boundaries between these fields of study. The holographic principle, which suggests that the information contained in a volume of space can be encoded on its boundary, emerged partly from studies of black hole physics and exotic space-time geometries. So while we cannot yet build wormholes or construct time machines, we can appreciate them as windows into the deeper structures of reality. They remind us that space-time, for all its apparent solidity and regularity in our everyday experience, is fundamentally dynamic and malleable. The same equations that predict the gentle ticking of atomic clocks and the precise orbits of GPS satellites also suggest the possibility of shortcuts through space and journeys through time. Perhaps most remarkably, these exotic predictions of general relativity continue to inspire new generations of physicists, engineers, and dreamers. They represent the furthest frontiers of our understanding, places where mathematical beauty meets physical possibility, where the rigor of Einstein's equations encounters the boundless creativity of human imagination. In contemplating wormholes and closed time-like curves, we glimpse not just exotic solutions to abstract equations, but profound questions about the nature of existence, causality, and our place in the cosmic order. As we continue to probe the mysteries of space-time, who knows what new possibilities might emerge from the marriage of theoretical insight and technological innovation? For now, we can marvel at how Einstein's elegant framework continues to reveal new depths of strangeness and beauty, showing us a universe far more flexible and surprising than our ancestors ever imagined. Now we come to one of the most mind-bending realizations in all of physics. The effects we've been discussing aren't just theoretical curiosities gathering dust in university textbooks. They're happening right now, all around you, woven into the fabric of your everyday life in ways that would have seemed like pure magic just a century ago. Consider for a moment the device you might be listening to this on. Whether it's your phone, your computer, or some other piece of modern technology, it's likely connected to the internet through a vast network of fiber optic cables. These cables, stretching across continents and beneath oceans, carry information as pulses of light. And that light, of course, travels at our familiar cosmic speed limit of roughly 300 million meters per second. But here's where it gets fascinating. When you send a message to someone on the other side of the world, that information doesn't arrive instantly, even though we often think of digital communication as immediate. There's a tiny but measurable delay as those light pulses make their journey through the cables, bounce through satellites, and navigate the global network. The speed of light, for all its incredible swiftness, still takes time to carry your words across the planet. This brings us to one of the most remarkable technological achievements of our time, the Global Positioning System, or GPS. Every day, millions of people rely on GPS to navigate unfamiliar streets, find the nearest coffee shop, or track their morning run. Yet few realize they're carrying in their pocket one of the most sophisticated applications of Einstein's theories ever devised. GPS satellites orbit Earth at an altitude of about 20,000 kilometers, traveling at speeds of roughly 14,000 kilometers per hour. At these velocities, special relativity tells us that time should be running slightly slower aboard each satellite compared to here on Earth's surface. We're talking about a difference of only about 7 microseconds per day, but in the world of precision timing, that's enormous. Meanwhile, those same satellites are experiencing weaker gravity than we feel down here, which, according to general relativity, should make their clocks run slightly faster. The gravitational effect actually dominates, causing the satellite clocks to gain about 45 microseconds per day relative to Earth-based clocks. Now, 38 microseconds might not sound like much, but GPS relies on incredibly precise timing to work. The system operates by measuring how long it takes radio signals to travel from multiple satellites to your device. If the satellite clocks were even slightly wrong, those distance calculations would be off, and instead of directing you to your destination, your GPS might think you're floating somewhere in the middle of the ocean. Engineers have to continuously adjust the satellite clocks to account for both special and general relativistic effects. Without these corrections, GPS would accumulate errors of about 11 kilometers per day. The system would be utterly useless. So every time you successfully navigate to a new restaurant or find your way home from an unfamiliar place, you're benefiting directly from Einstein's insights into the nature of space and time. But the influence of relativity extends far beyond navigation. In hospitals around the world, medical imaging techniques like PET scans rely on the precise timing of radioactive decay and the detection of high-energy photons. The equipment must account for relativistic effects to produce clear, accurate images. Particle accelerators, those massive machines that probe the fundamental nature of matter, couldn't function without a deep understanding of how particles behave at near-light speeds. Even the internet itself operates on principles that Einstein helped establish. The synchronization of computer networks, the timing of data packets, and the coordination of global communications all depend on having accurate, synchronized clocks, and maintaining that synchronization across a planet where different locations experience slightly different rates of time passage requires constant attention to relativistic effects. Perhaps most remarkably, we can now test Einstein's predictions with everyday objects. Physicists have demonstrated time dilation using commercial airliners, atomic clocks, and even laboratory equipment. In one famous experiment, researchers took atomic clocks on flights around the world and found that they had indeed gained and lost time exactly as Einstein's equations predicted. The precision of modern atomic clocks has reached almost unimaginable levels. Today's best timepieces are accurate to within 1 second over the entire age of the universe. These clocks are so sensitive that they can detect the time dilation effects of simply moving them from one floor of a building to another. Raise an atomic clock by just a few centimeters, and it will tick slightly faster due to the weaker gravitational field. This extraordinary precision has opened up entirely new ways of studying the universe. Gravitational wave detectors, like LIGO, use laser interferometry to measure distortions in spacetime itself. When massive objects like black holes collide billions of light years away, they send ripples through the fabric of space and time. These ripples are so tiny that they change the length of LIGO's 4-kilometer arms by less than 1/10,000th the width of a proton. Yet the instruments can detect them, providing us with an entirely new way to observe cosmic events. Scientists are now using networks of these ultra-precise clocks to study everything from the internal structure of Earth to the fundamental constants of physics. They're testing whether the laws of nature might be slowly changing over time, investigating the nature of dark matter, and even searching for signs of extra dimensions. But perhaps the most profound realization is that all of this extraordinary science emerges from what initially seemed like abstract theoretical musings. Einstein developed his theories not by building complex machines or conducting elaborate experiments, but by thinking deeply about the nature of light, space, and time. He asked simple questions. What would it be like to ride alongside a beam of light? How would the universe look if you could travel at the speed of light? What if gravity isn't a force but a curvature of space itself? These thought experiments, carried out in the quiet of his mind, led to insights that have revolutionized our understanding of reality and enabled technologies that now touch nearly every aspect of human life. From the GPS in your car to the atomic clocks that keep the internet running, from medical imaging to our detection of gravitational waves, Einstein's legacy surrounds us, and yet we're still only beginning to explore the full implications of his discoveries. Researchers are working on optical lattice clocks that could be even more precise, quantum networks that might enable perfectly secure communication, and tests of general relativity in the strong gravitational fields around black holes. The strange science of time continues to unfold, revealing new mysteries even as it solves old ones. Each breakthrough in our understanding of time's true nature brings with it new technologies, new ways of exploring the universe, and new questions that push the boundaries of human knowledge ever further. In this grand cosmic story, we find ourselves as both observers and participants, using the very effects that Einstein predicted to explore the universe that contains us, carried along by the flow of time that we're only just beginning to understand. Now that we've explored the intricate dance between time, matter, and energy, let's venture into one of the most mind-bending realms where Einstein's theories have taken us. We're about to drift into a world where time doesn't just bend or stretch, but where it might actually loop back on itself, where the very fabric of space-time could fold like origami, creating shortcuts through the cosmos that challenge everything we thought we knew about cause and effect. This is where we encounter some of the most extraordinary predictions that emerge from Einstein's equations, concepts so strange they sound like science fiction, yet are grounded in the most rigorous mathematics. We're talking about closed time-like curves, wormholes, and the tantalizing possibility that the universe itself might permit journeys not just through space, but through time itself. Let's begin with perhaps the most exotic prediction to emerge from general relativity, the concept of closed time-like curves. When Einstein first published his field equations in 1915, he likely had no idea that buried within those elegant mathematical expressions were solutions that would one day challenge our most basic assumptions about the nature of time and causality. A closed time-like curve is exactly what it sounds like, a path through space-time that loops back on itself, allowing an object or even information to return to an earlier point in its own history. It's not just about moving through space, it's about the geometry of space-time itself, becoming so warped, so twisted, that what we normally think of as the forward flow of time becomes curved into a circle. The first person to discover such a solution was Kurt Gödel, the brilliant mathematician and logician who was a close friend of Einstein's at Princeton. In 1949, Gödel found a solution to Einstein's equations that described a rotating universe, one where the fabric of space-time itself was spinning. In such a universe, Gödel showed, it would be theoretically possible to travel into your own past by following a specific trajectory through the curved space-time. Einstein was reportedly disturbed by this discovery. Here was his own theory, the mathematical framework he crafted to describe gravity and the cosmos, predicting something that seemed to violate our most fundamental understanding of causality. If you could travel into your own past, what would prevent you from creating paradoxes, from changing events in ways that would make your own journey impossible? But Gödel's universe was highly artificial, requiring the entire cosmos to be rotating in a very specific way. It seemed more like a mathematical curiosity than a realistic description of our actual universe. Yet it opened the door to a question that physicists are still grappling with today. Does the structure of space-time itself permit time travel? Or are there fundamental principles that prevent such paradoxes from occurring? The answer, as it turns out, is fascinatingly complex. Over the decades since Gödel's discovery, physicists have found numerous other solutions to Einstein's equations that permit closed time-like curves. There are rotating cylinders of matter that could theoretically drag space-time around with them, creating regions where time loops back on itself. There are configurations involving cosmic strings, hypothetical one-dimensional defects in spacetime that could, under the right conditions, create closed causal loops. But perhaps the most famous and intriguing possibility involves those mysterious tunnels through spacetime we call wormholes. A wormhole, in its simplest form, is a hypothetical structure that connects two distant regions of spacetime through a kind of cosmic shortcut. Imagine spacetime as a flat sheet of paper, and imagine folding that paper so that two distant points touch. A wormhole would be like poking a hole through both layers, creating a tunnel that allows you to travel from one point to the other without crossing the intervening space. The mathematical possibility of wormholes emerges naturally from Einstein's equations. In fact, some of the earliest solutions found to the field equations, discovered by Karl Schwarzschild just months after Einstein published his theory, contained what we now recognize as wormhole-like structures. But these early solutions had a problem. They were unstable, collapsing so quickly that nothing, not even light, could traverse them. For a wormhole to be useful for travel, whether through space or time, it would need to be kept open by some form of exotic matter with properties unlike anything we've ever observed. This exotic matter would need to have negative energy density, effectively pushing space-time apart rather than pulling it together as normal matter does. It's a bit like needing anti-gravity to keep your cosmic tunnel from collapsing in on itself. Now here's where things get really interesting from a time travel perspective. Even if we could somehow create and stabilize a wormhole using this exotic matter, the wormhole by itself wouldn't allow time travel. It would simply be a shortcut through space, like a cosmic subway tunnel connecting distant regions of the universe. But suppose we could manipulate one end of the wormhole, accelerating it to near the speed of light, and then bringing it back. According to special relativity, time would pass more slowly for the accelerated end of the wormhole. When the two ends are reunited, they would be synchronized in space but not in time. One end would be connected to the present, while the other end would be connected to the past. Step through the wormhole in one direction, and you travel into your own past. Step through in the other direction, and you journey into the future. This scenario, first proposed by physicists Kip Thorne and Michael Morris in the 1980s, represents one of the most carefully analysed possibilities for time travel within the framework of general relativity. It's not just science fiction speculation, it's a serious exploration of what Einstein's equations actually permit, carried out by some of the world's leading theoretical physicists. But as with all things involving time travel, the universe seems to have its own way of preventing paradoxes. Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics somehow conspire to prevent the formation of closed time-like curves, at least on macroscopic scales. Perhaps quantum effects near the entrance to a time machine would create such intense radiation that any attempt to create closed time-like curves would be automatically destroyed. Perhaps the exotic matter required to keep wormholes open simply cannot exist in the quantities needed. The deeper we dig into these possibilities, the more we discover that the universe has built-in safeguards against paradoxes. It's as if nature herself has a vested interest in preserving causality, in ensuring that effects follow causes, and that the flow of time maintains its orderly progression from past to future. Yet even as we explore these exotic possibilities, we must remember that they emerge from the same theory that has given us GPS satellites, gravitational wave detectors, and our understanding of black holes. Einstein's general relativity has been tested to extraordinary precision, and it continues to make predictions that are confirmed by observation and experiment. If the theory permits closed time-like curves and traversable wormholes, then we must take these possibilities seriously, even if they challenge our intuitive understanding of how the universe works. The study of these exotic space-time geometries has also led to profound insights into the nature of information and causality. If information could travel backward in time, what would that mean for our understanding of free will, of determinism, of the very nature of physical law? These questions push us to the very boundaries of physics, where quantum mechanics meets general relativity, where the microscopic world of particles encounters the macroscopic realm of curved spacetime. Some physicists have proposed that the resolution to these paradoxes might lie in the many worlds interpretation of quantum mechanics. In this view, time travel doesn't change the past. It creates new timelines, new branches of reality where events unfold differently. You could travel back in time and prevent your grandfather from meeting your grandmother, but you would simply create an alternate universe where you were never born, while your original timeline remains unchanged. Others suggest that the universe itself might be more forgiving than we imagine, that closed time-like curves might be possible, but that the laws of physics would somehow ensure that any changes made to the past were exactly the changes that had always been made. It's a kind of cosmic consistency principle, where the universe protects itself from paradoxes not by preventing time travel, but by ensuring that time travel always happened exactly as it was supposed to happen. These ideas stretch our imagination and challenge our assumptions about the nature of reality itself. They remind us that the universe is far stranger and more wonderful than our everyday experience suggests, and they emerge not from wild speculation, but from the careful application of our best theories about how space, time, matter, and energy interact. As we drift through these possibilities, these exotic geometries and impossible journeys, we're reminded once again of the profound mystery that surrounds us. Time, for all our equations and experiments, remains in many ways as mysterious as it ever was. We can measure it, manipulate it, and even perhaps travel through it, but its ultimate nature continues to elude our grasp, and perhaps that's as it should be. Perhaps the mystery of time is part of what makes existence so rich and strange and wonderful. Perhaps the fact that we can even ask these questions, even imagine these possibilities, is itself a kind of miracle, a testament to the extraordinary universe we inhabit and the remarkable minds that evolution has given us to explore it. So as we contemplate these closed loops and cosmic shortcuts, these wormholes and time machines, let's remember that we're not just exploring abstract mathematics or exotic physics. We're exploring the very nature of existence itself, the deepest structures of reality, the fundamental architecture of the cosmos that we call home. In the vast cosmic theatre, where galaxies dance across billions of years and light itself obeys universal speed limits, we arrive at a profound realization. The universe operates through patterns, rhythms, and connections that bind everything together. We've journeyed through the birth of galaxies from ancient darkness, witnessed how Einstein's revelations about time reshape our understanding of reality, and explored the intricate machinery of weather that breathes life into our planet. Each phenomenon we've examined reveals the same fundamental truth, that complexity emerges from simple, elegant principles. Time, we've discovered, isn't the steady metronome we once imagined. It bends and stretches, slows near massive objects, and refuses to let anything outrun light's cosmic speed limit. This isn't merely abstract physics, it's woven into the fabric of our daily lives, from the GPS satellites that guide us home to the starlight that carries messages from the universe's distant past. Einstein's insights revealed that time and space dance together as space-time, creating a flexible stage upon which all cosmic drama unfolds. Yet even as we grasp these grand concepts, we find ourselves grounded by the intimate rhythms of our own planet. Weather emerges from the same fundamental forces that govern galaxies: the movement of fluids, the transfer of energy, the eternal quest for equilibrium. The gentle morning fog that wraps around your shoulders follows the same physical laws that shape spiral galaxies millions of light years away. both arise from differences in pressure, temperature, and motion, seeking balance through beautiful, complex patterns. Consider how the moon, that silent companion Einstein used to illustrate his theories, also pulls our oceans into tidal rhythms twice each day. The same gravitational forces that bend space-time also lift and lower vast quantities of seawater, creating the breathing of our planet's edges. This isn't coincidence but connection, the universe speaking in consistent mathematical language across all scales, from quantum particles to galactic clusters. What emerges from our exploration is a picture of profound interconnectedness. The calcium in your bones was forged in the nuclear furnaces of ancient stars. The iron in your blood was scattered across space by stellar explosions billions of years ago. You are quite literally made of star stuff, assembled through processes that obey the same laws governing black holes and neutron stars. The atoms composing your body have travelled through space and time, participating in the grand cosmic recycling program that builds complexity from simplicity. This interconnectedness extends to our understanding of change itself. Galaxies merge and evolve over cosmic time, weather patterns shift with Earth's rotating seasons, and even time itself flows differently, depending on your motion and location. Change isn't disruption, it's the natural state of a universe in constant, elegant motion. The same principles that allow stars to ignite and shine also drive the evaporation that creates clouds, the pressure differences that generate wind, and the thermal currents that power storms. Perhaps most remarkably, we find that observation itself connects us to these cosmic processes. When you look up at the night sky, you're not just seeing points of light, you're catching ancient photons that have travelled across space for years, decades, or even billions of years to reach your eyes. You're participating in the universe's ongoing conversation with itself, receiving messages written in electromagnetic radiation and decoded by the intricate biological machinery of your vision. The scientific method that revealed these connections represents humanity's greatest achievement, the systematic pursuit of understanding through observation, experimentation, and mathematical description. From Newton's first insights about gravity to Einstein's revolutionary theories of relativity, from understanding weather patterns to mapping cosmic evolution, science provides a framework for comprehending our place in the vast tapestry of existence. Yet knowledge brings both wonder and responsibility. As we've seen with climate change, human activities can now influence planetary-scale systems. The same industrial processes that allowed us to build telescopes and weather satellites also alter atmospheric composition, changing weather patterns and affecting the delicate balance that sustains life. Understanding these connections empowers us to make informed decisions about our collective future. The beauty of scientific understanding lies not in reducing mystery, but in revealing deeper layers of wonder. Knowing that rainbows emerge from light refracting through water droplets doesn't diminish their beauty. It enhances it by connecting that moment of colour and light to fundamental principles governing the entire universe. Understanding that galaxies form through gravitational collapse over billions of years doesn't make them less magnificent. It places them in the context of cosmic evolution, revealing their role in the universe's ongoing story. As we conclude this exploration, we're reminded that curiosity itself may be the universe's way of understanding itself. Through human consciousness, the cosmos develops the capacity for self-reflection. We are the universe becoming aware of its own existence, questioning its own nature, and marvelling at its own complexity. Every scientific discovery, every moment of understanding, every connection we make between seemingly disparate phenomena represents the universe awakening to its own beautiful, intricate design. The patterns we've explored, from galactic rotation to tidal cycles, from time dilation to weather systems, suggest that beauty and order emerge naturally from the fundamental laws of physics. Complexity doesn't require a designer. It flows inevitably from simple rules applied across vast scales of space and time. The universe is not just stranger than we imagine. It's more beautiful, more interconnected, and more elegant than we could have dreamed. So whether you're watching clouds drift across an afternoon sky, feeling the pull of tides at the ocean's edge, or gazing up at the stars on a clear night, remember that you're witnessing the universe in action. You're seeing the same forces that shaped galaxies billions of years ago, the same principles that govern the flow of time itself, the same elegant physics that connects every atom in your body to the cosmic story unfolding around us. The journey of understanding continues, each discovery opening new questions, each answer revealing deeper mysteries. But perhaps that's exactly as it should be, an eternal conversation between human curiosity and cosmic wonder, played out against the vast, patient backdrop of space and time. Where galaxies spiral, light travels at its appointed speed, and weather dances through our skies in patterns both ancient and ever new. Picture this. You're floating weightlessly through the cosmic web, drifting past ancient galaxies whose light has travelled for billions of years just to reach your eyes. The universe around you is vast, quiet, and filled with stories written in starlight. But there's something else here, something that seems almost impossible to believe. Time itself is not what it appears to be. We've journeyed through the birth of galaxies, watched stars ignite in the cosmic dark ages, and marvelled at the elegant dance of gravity and light. We've seen how the universe evolved from a simple fog of hydrogen and helium into the magnificent tapestry of spiral arms and glowing cores that fill our night sky. But now, as we reach the end of our cosmic voyage, we must confront perhaps the strangest truth of all. Time, that most fundamental aspect of our existence, is far more mysterious and malleable than we ever imagined. Einstein showed us that time doesn't flow like a river, steady and unchanging for everyone. Instead, it bends, stretches and warps, depending on how fast you're moving and how strong the gravitational field around you happens to be. A clock on a mountaintop ticks faster than one at sea level. An astronaut orbiting Earth ages more slowly than their twin on the ground. And near a black hole, time can slow to such a crawl that what feels like minutes to you might be years to someone watching from a safe distance. This isn't science fiction or mathematical poetry, it's measurable reality. Every GPS satellite must account for the fact that its onboard clocks run slightly fast compared to clocks on Earth's surface. Without Einstein's corrections, your phone would think you're several kilometers away from where you actually are. The technology in your pocket proves, dozens of times each day, that time is relative, but the strangeness goes even deeper. According to Einstein's special theory of relativity, simultaneity itself is relative. Events that appear to happen at the same time, for one observer, might occur at different times, for another observer, moving at a different speed. There is no universal now that applies throughout the cosmos. The present moment, that knife edge between past and future that feels so immediate and real, is actually a local phenomenon, unique to your particular frame of reference. This leads us to one of the most profound puzzles in all of physics. Does time actually exist at the deepest level of reality? When physicists try to describe the universe using the equations of quantum gravity, the theoretical framework that attempts to unite Einstein's relativity with quantum mechanics, something remarkable happens. Time disappears from the equations entirely. At the most fundamental level, the universe might be timeless, with our experience of flowing time emerging only when we zoom out to the macroscopic world we inhabit. Think about that for a moment. The sensation of time passing, the feeling that we're moving from past to future, the experience of duration and change. All of this might be an illusion, a kind of persistent hallucination created by the way our brains process information. We are pattern-seeking creatures, wired to extract stories and sequences from the chaos of existence. Perhaps time is the story we tell ourselves about change, the narrative structure we impose on a universe that, at its core, simply is. Yet even if time is emergent rather than fundamental, it shapes every aspect of our lives. We age, we remember, we anticipate. Stars are born and die. Galaxies collide and merge. The universe expands and evolves. Whether time is real or illusory, it gives meaning to our existence. It allows for growth, for learning, for love. It makes possible the very thoughts you're having right now as you listen to these words. And there's something beautiful about living in the space between certainty and mystery. We know enough about time to build precise clocks, to navigate by satellites, to predict eclipses centuries in advance. But we still don't know why time seems to flow in only one direction, or whether the past and future exist in the same way as the present, or what happens to time at the event horizon of a black hole. These aren't failures of science, they're invitations to wonder. Consider the cosmic microwave background, that faint afterglow of the Big Bang that fills the entire universe. Those photons have been travelling for nearly 14 billion years, carrying within them the memory of a time when the cosmos was just 380,000 years old. When you look at that ancient light, you're seeing the universe as it was before the first stars, before the first galaxies, before anything resembling the structure we see today. You're looking backward through time itself, witnessing the infancy of everything that exists. Every telescope is a time machine. Every star you see in the night sky is showing you its past, not its present. The light from Proxima Centauri, our nearest stellar neighbour, left that star more than 4 years ago. The Andromeda Galaxy appears to us as it was 2.5 million years ago, and the most distant galaxies captured by the James Webb Space Telescope show us cosmic nurseries from when the universe was just a few 100 million years old. We don't just study the cosmos, we study its history, written in wavelengths of light that have crossed impossible distances to reach us. This interweaving of space and time is one of Einstein's most profound insights. We don't live in space and time as separate entities, but in space-time, a four-dimensional fabric where the 3 dimensions of space and the 1 dimension of time are unified. Massive objects like stars and planets curve this fabric, and that curvature is what we experience as gravity. Time isn't just affected by gravity. Time helps create gravity. Matter tells space-time how to curve, and curved space-time tells matter how to move, including how clocks should tick. But perhaps the most remarkable thing about time is how personal it is. Despite all the equations and experiments, despite the cosmic scales and quantum mysteries, time is ultimately experienced by conscious beings like us. We feel it passing. We mark it with birthdays and anniversaries. We divide it into moments and memories. We live in the perpetual present while carrying the past within us and imagining the future ahead of us. The universe doesn't care about our human timescales. Stellar evolution unfolds over millions or billions of years. Continental drift reshapes Earth's surface over hundreds of millions of years. The cosmic web of dark matter evolved over the entire 13.8 billion year history of the universe. And yet within our brief lifespans, we've managed to decipher much of this cosmic story. We've learned to read the language of light and gravity, to trace the evolution of galaxies, to peer back toward the very beginning of time itself. In a sense, we are time-made conscious. We are arrangements of atoms that were forged in stellar cores, assembled by billions of years of cosmic evolution, and somehow organized in such a way that the universe can observe and understand itself. Every thought you think, every word you hear, every moment of wonder you experience is the cosmos reflecting on its own existence through the lens of time. As we near the end of our journey together, floating here in the space between heartbeats, between thoughts, between the tick of one moment and the tock of the next, let's pause to appreciate the magnificent strangeness of it all. You are a temporary eddy in the flow of cosmic time, a brief pattern in the dance of particles and forces that somehow gives rise to consciousness, to curiosity, to the capacity for awe. The galaxies will continue their slow waltz through space long after we're gone. New stars will ignite in distant nebulae. Black holes will continue their patient work of sculpting space-time. The universe will expand and evolve according to the same physical laws that brought it into being. But right now, in this moment that belongs uniquely to you, the cosmos is awake and aware, looking out through your eyes, thinking with your mind, feeling with your heart. Time may be relative, malleable, perhaps even illusory, but it's also the stage upon which the greatest story ever told continues to unfold. It's the dimension that allows for change, for growth, for discovery, for connection. It's what makes possible the conversation we're having right now across space and time, as my words, spoken at one moment, reach your ears at another, creating a bridge between past and present, between one consciousness and another. So as you drift towards sleep tonight, carried along by the gentle current of time, remember that you are part of something vast and beautiful and mysterious. You are a child of the stars, a pattern in the cosmic web, a moment in the long story of a universe, learning to know itself. The same atoms that shine in distant galaxies flow through your veins. The same forces that shape the cosmos beat in your heart. The same time that governs the dance of planets and the decay of radioactive elements ticks quietly in your cells, marking the rhythm of your life. And perhaps that's the most comforting truth of all. In a universe where time can bend and stretch, where simultaneity is relative, and the flow of moments depends on your motion through space, there is still something unchanging. The fact that you are here now, part of this magnificent cosmic story. The speed of light may be the ultimate limit. Time may be stranger than we imagine. But your existence, brief as it is on cosmic scales, is real, meaningful, and connected to everything else that has ever been or ever will be. Time is a mystery we may never fully solve, but it's also a gift we get to experience, moment by moment, heartbeat by heartbeat, dream by dream, and in the end, perhaps that's enough. Perhaps the mystery itself is part of the beauty, part of the wonder that makes the universe not just a collection of particles obeying laws, but a home for consciousness, for curiosity, for the quiet miracle of awareness, contemplating itself in the gentle flow of time. Sleep well, fellow traveller in space-time. The universe is vast, time is strange, and you are exactly where and when you belong.